Good morning, everybody. This is lecture 6 of the machine learning in STEM lecture series this summer. What did we do so far in this machine learning course? On the one hand, we were reminded of all the theory behind the electron microscopy. There's only one topic still missing, that is diffraction, which we will be doing in the lecture after next. We did EELs, we did imaging, and depending on whether you are a microscopist or just want to learn about it, in the one case, you were reminded of the theory. In the other case, you learn the vocabulary. And so you can talk to microscopists and you know what they mean, hopefully. So we covered the basics. And so today we can do something more quantitative and analyze data. So today we quantify images, and from the machine learning aspect, we only did the EEL spectra at this point, right? So it's machine learning. Today it will be a little bit fuzzy, and beginning of the next lecture, we will do more and more machine learning and advance in the machine learning methods as we go along. So the TEM part is in the beginning, and then we go more and more into the machine learning methods. So that's for the overview of this. I want to encourage you to do your microscopy more quantitative. For the EEL spectroscopy, the key thing was to acquire at least your low loss or your current in some sense. Ideally, of course, you would calibrate your microscope to a point where you know what kind of number of electrons are in your signal. Why should you do quantification in EELs? We were already talking about it briefly. You want to have good training data sets with a wide application. So it cannot be that you only train your data on one material for one instrument for a specific day, right? So you want to have it trained, and then you want to have it applicable for everything. Also, you want to be able to compare it to theory. Once you have analyzed your data and you know what information is in there, you want to get the physics out of it. And so this is, as we heard in the first lecture, the key thing. So we not just want to do machine learning, we want to advance machine learning for microscopy so that we get some, so that we can learn some physics with it. So the problem and why machine learning is so necessary, and why I think, or many people think, that machine learning will be advancing electron microscopy, is that the electrons interact very, very strongly with matter. That makes it complicated, and it makes the information that we can gain very, very rich. So it's a very, very good opportunity for machine learning to advance the field. So that's where we are. In lecture 3, when we talked about the EELs, we already were talking about how we can quantify the EEL spectra and get composition, bonding, these kind of things out very, very accurately. And today we will talk about atom positions. We go on the microscope, we want to know where are the atoms, of course, in projection. If it's a two-dimensional material, it's not a problem. The projection is all you need. Otherwise, you have a projection of a three-dimensional material. So if you have the positions, can you do it accurately enough to determine strain? And strain as a tensor, in our case, we of course, because of the projection, we only can do the aerial or the planar strain that we get. If you just take a normal C-contrast image, so one image, you have a lot of artifacts, and you will not be able to quantify that very accurately. I mean, your error bars will be large, so you can still quantify it, but it's much better if you do it with an image scan. Why? You can get rid of sample drift. The noise in a single image can be averaged out. And if you do several scan image stacks, then you can get actually an idea of the scan distortions that are non-random and that you can then subtract. So that's what we're going to do today. We are going to take image stacks and try to get the atomic positions as accurately as possible, and we want to determine the strain of an image. And the question is, how accurate can we do it? We, as usual, do our analysis in Jupyter notebooks. They are available on the GitHub. We will make very strong use of the SID-Pi dataset format, and we will store that in the PyNZ format. The whole microscopy ecosystem is there so that you can use any kind of method developed for electron microscopy, SEM, neutron scattering, whatever, SPM, and without any kind of problems. You have it in a format that you can directly use these other methods. So that is a microscopy ecosystem that we are all working on here. And so we'll go through that in the notebooks again. So we did already quite some of that, but if you work with real data sets, and we will see the necessity for that a little bit more clearly, hopefully. So if you have a stack of images, you can make a rigid registration. So in the end, it is a cross correlation from one image to the next, and then you can determine how much of a drift did you have. This is one of the stacks I acquired. Actually, this one was exactly acquired by Matt Chisholm. And you can see now what kind of drift did we get in the X and in the Y direction, right? So here's X and Y. So that is the X, this is the Y. And let's look at the quantity of that. So we have about we have 25 images that we acquired relatively quickly. If you acquire an image stack, the single image stack should be able to be cross-correlated. So there needs to be some information in there in the Fourier transformation, so you can check that out. It, on the other hand, should be fast enough acquired so that you have very little drift from one to the other. In our case, within 25 images, we got a total of 3 in the Y and 2 pixels in the X direction. So that was very, very stable. And you cannot normally reach that kind of precision or stability with a side entry holder. So I did this here this rigid scattering, rigid registration with sub-pixel accuracy, and we will see that Z is actually a complete overkill, and the less you do to your data, the closer you are to the original ones, the better it is. So, do you have to correct that? The answer is yes. You do actually have to correct that in order to improve your quantification. So we need stacks of images with low sample drift. Low is relative, but it shouldn't be more than 1 or 2 pixels per frame. In the ideal case, of course, even less. The fit through that will allow us to quantify our drift. So there is some jitter involved here, and the jitter is in the order of some picometer. So for a 512 by 512 image, you can already imagine this is not going to be relevant. So sub-pixel accuracy in the drift correction, the rigid drift correction, is not necessary. After that, we do non-rigid registration, a daemon registration, and we will do that in the notebook. Okay, so I'm not going into that now, but oops, I'm on the other side. So here we have distortion correction, and we did that after we did a rigid registration, a non-rigid registration. We did atom finding, we refined the atom positions, and then we find the unit cells. And since we know exactly how big a unit cell should be in a bulk material, we can then undistort this, this image. This is a bulk data set, 25 images, and we did that. After the analysis, we can see actually what distortions we had before, right? So we had a standard deviation of 0.8 picometer and smallest and longest side. So the pixel size in this is 14.6 picometer. So the question is, can we get sub-pixel accuracy absolutely in our image stacks? So we go for the squares, and after we do this analysis, we get the distortions, and so the volume of them is extremely accurate. Well, what we expect. So we took that image, we determined where the unit cells are, we undistorted according to these distortions that we just had here in this data set here, right? And of course, it's as good as it gets, right? So the doesn't tell us anything. That's the point, right? So it works. That is the main thing. And however, what we did is we did it on the unit cell, and now we can determine how accurate can we determine the titanium. Now we know where the unit cell is squared. How accurate do we get the titanium one? And again, this is our pixel size, 15 picometer. And clearly we reach sub-pixel accuracy. So nice, but not surprising again. The next thing we want to do is we want to apply that to another data set. So this, we get a distortion matrix from bulk material, and then we use another bulk material and apply that. To right afterwards or after some time to the same material, but a different data set. And we want to determine strain. And strain is, of course, one of the often misunderstood kind of terms. What does strain on the atomic scale mean? The definition I want to use is the definition based on the unit cell. So we have projection of the unit cell, and the blue one is just a square, right? So you can then have a tetragonal distortion, you can have a rotation, and you can have actually also a shear. So we deform the square in different direction, and the rotation itself is, of course, not a strain, only the shear component of that. So that is what we are after, how square is, in our case, strontium titanate, or how much deformed is any of the unit cells. So you can do that on any unit cells, and what we're going to do is we're going to use highly reliable data sets, and we will use graph theory to get to this point, to analysis set. So the shear distortion is now much larger, and so this is now tetragonal distortion is very low, and the shear distortion is a little bit larger than before, so that is in a different one. So that is still the original one. So now we go and do set on a different data set. One of the important points here, if you use another data set, is I wanted to go back to this one. If you take the sample out, what you usually have is you have a blanking on the very top of your microscope, so that will change possibly some of the electron optics. What you should not do is you should not change the rotation of your scan. The scan coils are not perfectly orthogonal, and the manufacturer of the electron microscopes have an engineering alignment that compensate for this non-orthogonality, and again, that is not going to be perfect. The magnification should be the same, can be changed within a few, with moderation, but the closer you are to the same magnification, the better. And within a short time frame is better than waiting for a week or two. You don't know what happened to the microscope. So ideally, you take some bulk data sets, and then you go to the area of interest to analyze it. If you want to, in our case, we want to see how good did we do that. So we have now a deformation matrix, and if we do it on that same image, we know our undistortion works perfectly, and we'll see how we do that in the Jupyter notebooks. But here now we use a different data set. This data set, as you can see, has a different drift in the X direction. We have almost no drift. In the Y direction, we are over here, right? So in the Y direction, we have a little bit more drift. So how much more? 1 pixel more in 25. So in both cases, it was basically negligible, and we can sums this, do our rigid registration and so on, and this is a result of that. And then I do my undistortion, and I look how good and how stable is my microscope. And now we are really asking for our error bar, right? So the medium area is, instead of 0.3904, 3903. So with a standard deviation of 0.0, yeah, okay, a few picometer, right? So that is 2 picometer squares. So suddenly we are certainly in the sub-angstrom accuracy. If we look at the shear, the angle deviation, so we have a square, so it should be 90 degrees, right? We have a 1 degree deviation with a standard deviation of 4 degrees. So obviously not really quite as perfect as the relative distances. We only used the center part of the images, so the part on the side we did not get. The tetragonal distortion can be determined by the smallest and longest side. And again, we are subpixel accuracy, standard deviation of 13 picometer. That is okay. And in the other case, say 7. So this is not the atom position. This is the unit cell determination, right? So our accuracy for a single unit cell lattice parameter is in the order of 1 pixel. And since we have strontium titanate, and we did that only on the strontium columns, so we have the titanium oxygen columns, I think it was multiplied by a factor of 100, so that you see this deviation. It's relatively random all over the place. Where it is too small, we don't have one of these arrows. So there is not a consistent one. There is one across the diagonal where it's especially bad. And so now we can see how accurate did we do that on a different data set, right? Let's look over here. So in the average, we are accurate to about 5 picometer deviation from the center. It's actually not clear whether that is a materials property or not, right? So it's too small to call. On the other hand, we saw when we did it directly on the image, we had something like 2 or 3 picometer. So still okay. The standard deviation is 12 picometers, so again, subpixel accuracy. And you only can reach this kind of precision in the single-digit picometer if you oversample your images, and if you know your drift and cancel that part out, and if you have a very stable microscope. The strain, tetragonal distortion, not surprisingly, a little bit worse, right? So, but not a lot. So again, we have reasonably quantitative data, and something that should be square is not quite, but that gives us our error bar. That is the key thing here. Now we apply that to a data set. So we have strontium titanate in the top right corner. We have LMO, lanthanum manganese oxide, and then PCT. And we want to analyze that. So strontium titanate is probably about whatever over there. We used the same magnification, the same everything, same rotation, very important. And so now we did that twice so that we can determine our error bars. And now we can analyze this kind of interface. And we did exactly the same thing, right? So we did tetragonal distortion, shear, and so on, squareness, area, and we can determine all of these different things here. So this is the idea, and we can see in the strontium titanate we did very well, and so we see that PCT is clearly distorted. So we have a tetragonal distortion here. Squareness is then, of course, gone. Shear is the same all over the place. And of course, tetragonal distortions is quite obvious. The strain must be only directional. So we see here the smallest side are always the same. So we have that in the same within our error bar, right? So we have only a tetragonal distortion, and this distortion is an elongation away from this interface. And so we can just read that out directly from our plot here of the strain, of the different strains. So there's no shear that we can see. It's only tetragonal distortion. So that's exactly what we expected. And then if we look here, we have basically no distortions, right? And in the PCT, we have a distortion. And now we can analyze the deviation of the titanium oxygen from the center. And of course, PCT has a large deviation. We see it has something like a circle here. And if you look more carefully, then you see here is actually a step in the interface, and that is where you have this large deviation coming from, and it's not very linear on an interface. It's a larger view of that. We can look at that a bit more in detail, right? So we have the tetragonal distortion. It's where we have a step on the interface. The tetragonal distortion is minimized, right? And then it's larger on the other side. We have large deviation from the center of the titanium oxide. So we have a large polarity here. This is relatively benign, so there's not much of a distortion in the STO. And actually, if we analyze this layer of the LMO very carefully, then we see that that is slightly compressed. So non-distorted strontium titanate, slightly compressed LMO, and then a highly distorted and therefore very inhomogeneous polarities or deviation from the titanium oxygen columns from the center. So I hope I showed you that if we do it right, we can quantify our STEM images in terms of strain. The key thing is, of course, as with anything in electron microscopy, we can do that with spatial resolution, and we define our strain on the atomics unit cell. So We need error bars, otherwise we don't know how good we are. Error bar of a few picometer is in the mega to gigabyte, gigapascal range, so it's relatively high stresses that we can access to only. The data sets are limited by the strain determination. So we will see what determines that strain determination, and that is how accurately you can determine your atom, and then how accurate or how stable is your microscope. And there are several parts of your microscope that will not be more stable than they are right now. And we get very nice images with our coherent probes. Cold field emitters get a little bit more current than the Schottky emitters, but for practical purposes, the acquisition of the data sets is key. And of course, the sample stage has to be as stable as possible. On the neon, as on any of our other microscopes, we actually get in the order of a pixel per frame drift, but we have to wait for a fair amount of time before we can do that. So generally, it's about half an hour before the whole system settles down to something that we can use. With that kind of data sets, of course, you can do a lot of things, and we have data sets that can be quantified. It doesn't matter where you get them from, right? If you know the drift is subpixels, and we will see that we can determine that still very nicely with the non-rigid registration. We should include noise analysis if the noise is in the order of the Schottky noise, and Poisson noise of the Schott noise of the quantum mechanical process of excitation, then we are on the limit of that, but we will see that this noise is actually what's limiting it at this point in time. A key thing would be to get faster to our experimental conditions that we have and get our data sets faster. So moving around to the different areas and get data sets, and not forget to get some of them. So automatization and AI will be key for that. And then you have a data set that is universal, usable. You can do your diffractograms, so you can compare it to diffraction data. So you can compare these ones, all of the different diffraction data from X-ray diffraction, neutron scattering, you can put together. You can get the images on different length scales, and ideally you have very reliable clear understanding of what's going on in your material, in your samples. So that is basically the goal. That's where we want to end up with. And there are quite a few steps that you have to go to get to something like this. And we will go through most of them. So we have to do the the registration accurately. Then we have to determine the atoms and the unit cells from that. And we will learn how to do that. Once we have said, we can get distortion matrix. The way to get the unit cells and the strain is the way I'm doing it is based on graph theory. Graph theory and machine learning is also directly related in many aspects. So that's where we are at this point. if we go and start one of these notebooks, so we are in lecture 6 now. And so I think that was eels. Then we did some linear or PCA and statistics and k-means. So simple machine learning algorithms here on the spectra. And we will use the same one again now. And so we had some TEM lectures, and now we are here on this one. So if we use the first one, that is, the first step is register your image stack. That works on any kind of stack, as long as it's stable enough. And if you open that in Colab, okay, then what you have to do is, as usual, you have to load all the different packages. Not sure that's the newest one. The Google Colab has one problem that we will see here in a second. And that is that it does not really allow the IPython widgets event manager getting fully access to that. And that is why I'm going to show you the whole thing also on my own computer, so that we can see the effect of the widget registration. It's much nicer if you have that like a movie showing. Okay, so I installed it all. Now I load them. Oh, that was quick. Okay, and I download the image stack dataset. And over here in Google Colab, went to that. So I have now example data, and there should be now my stack images here. So we are in the open file part. I'm using my file widget, so I go into the example data. It's showing me the original name. So this is a neon file recording. So the sci-fi reader package in microscopy allows you to read any kind of microscopy data files, SPM. So if you're not happy with any of that, put an issue on GitHub in sci-fi readers. We select that as main, and then we load that dataset. The problem here is if you go to the run, it does not run, and I don't know why, but I will find out on that. If I do the same thing over here, and that may be giving you time to catch up. Just started it, and I should be here in lecture 6. Yeah. And I open with the same one. So it runs obviously also on a Windows machine. It's on my own one here. This is not the one. Where is my, what's it called? Recording of SuperStem. Here we are. We select that as main. I load the file. And now I can have that run here. And it runs through that. Let's do that with this one. And we can see how we have very little movements here, right? So that we have a drift, and when we jump back from 0 to 1, so we have this shift of 3 pixels, and we don't want that. Under normal circumstances, people would probably just average that and say, okay, it's good enough. The problem is you will have slightly elongated, that's in the other direction, I think, atoms. And the key thing is, if you align a microscope, you want to have round ones. So we do a rigid registration, which is fairly fast. And so now when we run that, we don't see this anymore. So we jumped actually from one to the other one. Let's move. I have not to jump that back, have that jumping backwards and forward here. Okay. Let's zoom in a little bit. And let's talk about why it doesn't make any sense to go to subpixel accuracy here. As you can see, even though the whole frame is extremely stable, the atoms dance around a little bit. And they dance around. If we have here spot, right, you can see they jump around by a pixel or even more. So this is not something that would benefit the accuracy if we do it better than 1 pixel, because then we would have to interpolate that. And so we want to avoid interpolation as long as possible. So what we are going to do is we are leaving that there. And this random positioning here are, of course, instabilities in your scan. Some are digital. Most of them will average out. Some of them might be are reproducible, and that's the ones that we want to determine with our distortion matrix. So we want to separate these two parts of instabilities out. The random ones would be possibly, or for example, say the eddy currents. So we have a beam going through a magnetic field, and this electron beam is a current. And so you will introduce currents back into the magnetic material, so your poppies, and that will disturb this. So this so-called eddy current is one option. Then, of course, you have slight charges on the sample, slight charges within the microscope, and all of that would be random, while the distortions in X and Y and in the scan, possibly the amplifier, would be reproducible. So the random ones we can average out. That's why we use a stack. That's another reason why to use a stack. So how good was it? So of course we can just look at the drift and determine our accuracy. So is it worthwhile using this image stack? If you have much more than a pixel per frame, depending on how big your frame is, in our case it's 512, then you can think about, should I undistort from the rigid point of view, from the rigid registration point of view, my image before I go on? That could be done. That will take you certainly longer than waiting for half an hour on the microscope. So I'm preferring to have a cup of coffee instead of doing a lot of things on the computer. So everybody's choice, but the idea is this is a good data set and nobody will complain about that kind of stability. Okay, so after we did that, we can now add that up. So we sum this rigid data set. So that's the advantage of the SITPy data set, all of these different functions that you used from NumPy are natively implemented, and you get back a SITPy data set that you then can just plot. What I'm interested in is the contrast. How good of a contrast did we get? And so we have to think about what is contrast. And you can look at this definition that is usually used for contrast. So it's a standard deviation of an image, and it's divided by the average of the image. So that's what we usually used as contrast, and we get a contrast of 0.36. So this is a very good data set. So if we do now a non-rigid registration, before we do that, we have to look at, say, what do you do if you do a subpixel accuracy? So I had that in my slides, so I thought I'll share that with you. There is something called phase cross correlation in say SciPy spatial, I think, and you can upsample your cross correlation. So if you do a normal cross correlation, and that is what I did, I just do a normal cross correlation, and you can see from one picture to the next. That's how I do that. So one picture to the next, and obviously if it goes all over the place, I'm not using any of this. So it has really small drift from one image to the next. So, and then I get cross correlation here, and so with pixel accuracy, you can determine where your thing is. And here in our case, it's very little, right? 1 pixel. If you upsample this kind of cross correlation, then you can determine the maximum with subpixel accuracy, and then you can do your drift correction with subpixel accuracy. Again, then you need to, in order to align the images, you have to do some interpolation between the pixels, but we will do an interpolation between the pixels anyway, and it doesn't help you against the small dancing of the atoms around. So that's, we do now a rigid registration, so we save that because we might want to use that again. So now we do a non-rigid registration. That will take a while. This is a so-called daemon registration. Let's see how fast it is on my computer. On this, so it's 5 minutes. So it's about as long as it is on Colab. If I don't have Zoom running, it's a minute. So you can run that on the supercomputer center, and then it's almost instantaneous. I'm using the simple ITK routines with daemon registration. So what are we doing there exactly? Let's go back and look at this image. So this is the starting image. And because I averaged over the whole stack here, I can assume, or that the assumption is now, that the atom stands around randomly. So all the random distortions are averaged out, and my position of the atom is where the atom position is, or where the contrast in the image is. Okay, I can't do anything right now because it's doing my daemon registration. So I have a contrast in the image, and so this is where it's averaged out, and so the daemon registration now determines the distortions so that it is fitting the averaged image. Simple ITK is used in the medical imaging. So you get an MRI scan of your brain, so that is the typical data set. Say, put it back to a standard brain, whatever that means. And then they can compare any kind of deviations that might be happening. So they use it for unscaling. So we use it to get each single frame, the atomic columns on the average. And that is an interpolation. There are different parts that you can use, or different functions that you can use with this daemon registration. So here, if you go to the appendix, while doing that, we can go through that a little bit. So we do a daemon registration. It's called diffeomorphic daemon non-rigid registration, if you want to be super precise, by simple ITK. And so here are the relevant links for that. So we do the reference image. And in our case, the reference image is registered stack summed over all the images. If there is a problem with one of the images, of course, you can throw it out, right? And then there are different ways to determine the deformation matrix. So with respect to that, and that is deformation matrix is then used to transform the image. And there are different ways of doing that. So you can do it linearly with a spline, with a Gaussian smearing, Hamming window. So they have different ways of transforming that. And if I do that for different ones, then you can look at the roughness, accuracy of that, right? And you see that the fastest one that does not introduce any kind of artifacts is actually the B-spline. That's the most accurate one for our types of images. And so that's what I'm using. So you're very welcome to try all of those out. We are still waiting here. Bar here tells us we need another 12 seconds. So once we have that, it plots it. And if we let that run now, you don't see anything, right? Okay, so it worked. If we zoom in here, let's see what happens. We have to zoom in quite a bit. Now we see that the only thing that is changing is the noise. And the atoms are, of course, very round. So everything is pushed back together. So we get a very high quality image if we average this kind of stack now. So this is as good as you can get it. And we can look now at the contrast, and from 0.36, we get 0.38. So we increase the contrast. Contrast increase is if you are using a little bit more noisy data. And then you get a much better contrast increase. but you will get in contrast in that kind of order if you do a fair amount of stacks with the daemon registration. So the noise is basically gone. And then we can log that. So we have our data sets. That is just a dictionary. So we put another one on here. And so now we have dataset chooser. We can go for any of the ones we have and can look at them again if we want to. So that was the rigid registrated ones. And so we can just view them as we want. And we can save that file. Just save it to the same area where we had that. And we can check it out where we put that. And ideally, we would close that so that we can use it in a different notebook. Now, the way our Google Colab works, we cannot use this file because now we would have to upload it because I have it on my computer. If you did it on your computer and you start Colabs and it is actually a new instance, then you would have first to transfer it either to your computer and then backup. So we're not going to do that. What we are going to do is we are using ones that I did before for the next notebook. But if you have that, so we can go our non-rigid registration and we can do CFUE, can look at that and can do the power spectrum and do whatever we want to. If we look here, we are about here. So 1/14 nanometer is my resolution. So it's about so it's about 70 picometer resolution for this kind of image. So good enough. As I said, now we are trying, now that we have this really good data set, we're going to analyze it. And that means we undistort all the random intrinsic distortion. So we got rid of all the random ones, drift, and so on. And now we want to have the systemic ones. And we do that in Colab. Loading. Okay. We, again, as I said, we have to run that. And what we want to do in this notebook is we want to determine the distortion matrix. So that's all we're going to do. And we have one other notebook still where we are doing the graph theory, and that's where we also, where you can see where the strain and so on are determined of an image. So because we have strontium titanate, I just said, oh, okay, this is also strontium one that makes it the unit cell. In the titanium oxygens, I determine how far away it is from the center. You have to sort them first, right? And that's where we are, that's what we are going to use graph theory for. So we have that imported. This one we don't need. It's left over from my computer. We have that installed. We now determine, download our image stack. So we should have that now in the example data. Yep. So it's a registered stack. In the file widget, we load it, registers STO stack, select this main. Last time I forgot how to do that, right? So, and then we are loading set. Here's our stack. And as I said, normally this doesn't work in most of the things. Okay. Anyway, so we have to find now the atom positions. And even though this is a good image, it's not going to be good enough. So first of all, we sum it. Now we have an image. And what we do with this image, we do a Lucy-Richardson deconvolution. And for that, what you have to do is you have to input how big is the atom in that view. Okay. In our case, the atoms are about 90 picometers, and the Lucy-Richardson deconvolution is relatively fast. And you can argue it is. So Lucy-Richardson deconvolution is based on maximum entropy. Could be a machine learning, could be not. We don't care, right? We use it. And the effect, of course, is what we are after. If we zoom in here a little bit. No? Okay. Doesn't like me. Good. Whatever. So instead of these really big atoms, we get now very, very small blobs. And we save that Lucy-Richardson deconvolution. And we can now, in the image choice, determine that we want to have the Lucy-Richardson deconvolution for our blob finding. And obviously, this is very, very fast. Push here. And it's very reliable. Okay, this is a good data set, no problem. So this is the quality of that. And so please note, it works for any kind of atomic resolution image, because all it does is blob finding. So there are good reasons to do atom finding with atom AI on the microscope, because you want to know when you're on the microscope, where are the atoms, and you don't have very good images, it's very noisy and so on. On a good data set, you always will get them, okay? And you will get all of them, or at least the relevant ones, and I'll show you how to get the rest. So we have the atoms, and then we log them. And because we want to have sub-pixel accuracy, what we want to do now is we want to fit an atom in there. And we want to do that on the non-rigid registered data set. So we fit a Gaussian into each of these atoms. We are using only the center part. And okay. Should have done that. And we have the atom refinement, was there for a second. Not sure what my Google Colab does. So we found our atoms. Now we have to classify them. So what I want to do is I want to jump through the atoms and I look at them as a graph. Each atom is a vertices or a node of a graph, and the bonds are the edges of the graph, so the connections. Or I use only the unit cell, in which case the unit cell side is my my edge of the graph. And for that, I need to know what kind of material it was. and I just load the strontium titanate from my kinematic diffraction package of PyTemlib, and then I again look what kind of image I want. I want to do that on the Fourier transformation, it's the original one, and I put my atoms on top, so that are the refined atoms now. We don't see that very well. Let's zoom in a little bit. Maybe the zoom does work now on my screen. Okay, so we have the atoms determined, all of them. So the Lucy-Richardson deconvolution worked. What we do now is we want to know in the diffraction pattern. Oh, we did that already, right? So it's all the same stuff we have done already. So you see why I went through that. Now we don't have to worry about it anymore. We just do a blob, detection on the Fourier's part. And now I do what I did last time. I fit the diffraction pattern of strontium titanate onto these experimental ones. So the orange ones are that. And again, this is just matplotlib. So you can use the color bar and change your positions, your intensities around. So, what did I gain with that? I got my rotation. So I know in which orientation my unit cells are. Let's go through that. And I know actually what kind of scale we have, and I change my scale accordingly. Again, we did that last time. Okay, here is my change of scale. You can see that the change of scale is very small, standard deviation of 0.072. So we have a very, very nice data set. So there shouldn't be much of a distortion. And now we have it on an absolute scale for our strontium titanate. So nothing is happening anymore. And what we want to do is we want to run through that with, I sort of had an image of them. And I have to select one. If you don't select one, the program doesn't work. So I haven't done it that way. So you have to select one. And then it tells you which one you have selected, just to make sure. And now we walk through this atom positions that we found with the unit cell. This is our unit cell, and this is the steps that I want to run through my atom positions, right? I know where the oxygens are. I have my, what I get is then I always get my origin of my projected unit cell. And the projection is done as we did. We're gonna go through that in before. So I determine up here in my experimental condition my zone axis. So it's a 0, 0, 1. Put it here. Okay. This is my zone axis. I have determined strontium titanate, no mistilt, and I have my excitation error, which gives me how many spots I get, right? It's a thickness equivalent, and it gives you a maximum amount of HKL. So we determined the zone axis. We could have done that from the diffraction pattern. So obviously it could be optimized with machine learning. These things could be learned, right? And so again, we hop now through our atoms in steps of unit cells. We get our origin, and if we have the origin, we know where the other position should be. Okay. And I do one more thing. I jump to the next atom. Now, blue was maybe not the best one to determine. So I start up here and then jump over here. But I also know where the ideal position should be, right? Because this is the nearest one. So I jump over here, find the next nearest neighbor. And I do that with a breadth first search. So again, I steal it from graph theory, how I'm doing that, how I run through this kind of nodes. And then I have two positions now, one where the atom is and where it should be. And this is what I'm using. So this is the unit cell, but I'm also can tell you where should the titanium oxygen be, and then I can tell you how much it is deviating by just looking at it. So that's what I did before, but after I did the deformation matrix. But we see already how powerful that is. I sorted already all the atoms depending on what kind of atomic what kind of elements there should be. And now I can make histograms of these atoms, intensities. I can see whether one is missing or not. So I have all the tools already in hand here. What I'm doing is I'm making this sublattice and store them. And then I determine how much the inferred position is from where it is supposed to be. So now I have two sublattices, and that are my ideal ones. So they are far off, obviously, but I also have the ones that are perfectly aligned. And so the okay, getting there. So here are my strontium columns, the titanium oxygen columns. I also know that here are the oxygen ones, and I could also do these sublattices. Would be very, very easy to do, right? But obviously in this C contrast image, I don't have any information about them. But with an MDF or some other ones that is associated with it, I could. I store that, and now what I want to do is I want to determine the distortion matrix. I have the information of here's an atom and it's supposed to be over there. So this is part of a deformation matrix. But what I really want to do is I want to determine that for each pixel. What I'm doing is I'm using a Voronoi tiling of all the atoms. So I have an area that is unambiguously associated with one atomic position. And I have the neighboring ones as well, so I know how it is distorted. So what I'm doing is I undistort that Voronoi cell and then place it where it needs to be. So I can get a position for each single pixel at the right scale. And I can determine what is my, for each pixel that I can evaluate, because I have a Voronoi cell. So on the sides, you see, I cannot determine Voronoi cells. And also there is some deformation. So in the center, I have very little deformation, and you see to the bottom right and the top left, here we are. We have more and more deformations as we go along. The deformations go in this direction, so they flip in the middle. And in the middle, of course, because there's very little deformation, which direction it goes is undetermined, but it basically goes in this direction and that. So we have deformation in that direction. In the very first lecture I gave, so lecture 2, I told you it's very important to determine which one is the fast and the slow one. And you can see now why, right? So we have to be very, flipping that would make the whole thing more difficult. The deformation matrix, for each pixels, which are 2 dimensions, gives you another pixel, which is another 2 dimensions. And if you use that deformation matrix, you can undistort your image. We use the image that we just had, right, in the deformation matrix. And we interpolate that. So SciPy spatial has an interpolation. And then we can run the extent. And this is now the perfectly undistorted image. And the same distortion matrix you can now use on any of the other non-rigid registered data sets that you have, at least from the same week, from similar specimen, and so on. So depending on your microscope or the microscope you're looking at, this is what you can do. This is something machine learning can probably determine for each microscope. What are the different deformation mechanisms? If you have enough data sets, then it can learn that. We can log this undistorted image, of course. There's not much value to it. Oh, one thing I forgot. I plotted the atomic positions of the perfect atoms. And so you see, there is no wonder that that is perfect, right? Because I'm using that to undistort it. And then, of course, they are at the right place. And but it gives you confidence that all the undistortion was done and you didn't mix any of the different dimensions. Okay, so we went through this whole notebook now. And if you use this distortion matrix on any other data set, get an undistorted, perfectly nice image that you can quantitatively determine. So we set shear to about 1 degree and atomic unit cells, so stress to about 5 picometer on our data set. And you can determine that for each of your own data sets as you want to. But what we did use was a lot of graph theory. And this graph theory is much more powerful than just determining that. And so we want to go through that very quickly because, 40 minutes, so it should be fine. Let's go through that and go through the graph theory. It's a notebook. And we open it in Colab. We download all the different missing packages that we need. In my case, for PyTimlib. I want to warn you, if you watch this video some time from now, we are going to move a lot of this graph theory stuff over to microscopy, but I might still have it linked into PyTimlib, so that's all you need. Obviously, this graph theory is important for a lot of different imaging data, right? Doesn't matter how you determine your blobs. Once you have them, you want to categorize them and learn what they are. Okay, so we are done. we load the downloaded samples, packages. Okay, and so now we are looking for graphs. The atomic positions or projections. So we have a planar graph, which is good to know. Geometric or planar graph is what we see. The vertices or nodes, right, or the atom positions. Generally, the edges are either, as we saw, the unit cells or the bonds. And if we look into organic chemistry, what we want to see most of the time is rings. So what we want to look at, or we want to look at these atomic positions as a ring graph. So unit cells are basically rings, and now they can be six-fold or four-fold, whatever, right? Rectangles, whatever they are, the triangles, any of those we are okay with. And part of that comes from chemistry, where they want to recognize benzene rings in randomly oriented molecules or whatever, right? So what we restrict ourselves is convex polygons, right? So there are no other ones. So we want to have a convex geometric graph of rings. And we apply that to all the different Bravais lattices that exist in 2D, right? And they look like this. These are our different Bravais lattices, right? So square, FCC, and so on. And here are the unit cells in here. This is sheared. So, and to determine that is a little bit more tricky than it looks like, actually, because what I did here was just the Voronoi, and let's do that again and see what the Voronoi tiling does to that. It actually gives you this kind of spots, and the positions then between them would actually be like this. But this is actually not really bond. And so let's look at that a little bit more closely. If I now look at the Voronoi vertices, so I had two here, and these are too close together. Let's think about them as, now we do crystallography, as interstitials. If you have two interstitials and they overlap, obviously it's one big interstitial. So that's what I'm trying to do here. I'm trying to get overlapping interstitials. And if they overlap, I use them as one. And so in this case, it's non-overlapping. And in this case, I say they're overlapping. And so, so for a hexagonal system, I get bonds in all direction, obviously, and in an FCC case, I would get them. Is the middle one missing? Okay, so that gets me extremely close to what I want to see from a projection of a crystal. So the honeycomb versus the hexagonal diamond, all of them are now exactly as I want them for the rings that I want. Let's look at the honeycomb one in detail. So this is just now a whole bunch of graphene atoms, molybdenum diselenide, whatever you have, right? So we have this honeycomb kind of lattice. And what I want to do now is I want to show you the power of this kind of ring determination with for defects. where are my dislocations, what kind of dislocations are there, what kind of defects do I have, and so on. And so I make a stone walls effect, and I just, these two atoms here will be rotated. And if I do my analysis now, without any kind of fancy thing, so they will make me a mess, right? And I will see immediately where the defect is. Okay, it could be enough, but we want to know which kind. And so the desired graph is, of course, this one. I want to color them. I want to have all the hexagons in red. I want to have my 7-fold rings, different colors than the 5-fold rings. And so this is what I need. And then I actually get the reliable bonds for that as well, because bonds are around the convex ring here. That must be my bonds in the projection, right? And so this is now a way in 2D or 3D to get bonds independently of how far away your atoms are. This is really nice. The theory behind it is relatively complicated. And so, but you can make all of your crystallography based on the interstitials. So they are equivalent. But that would be going too far here to go into that. And so what did we really do? We looked at all the, if there were no vertices, where we have only one, we don't plot them, but where we have several of them, we plot them, and then this is the center of our ring, and this ring is then colored depending on how many vertices it has. So the cyclicity is just the number of vertices around there. And I also can now determine how many nearest neighbors does each atom have, right? So this one has 6 nearest neighbors, and I just know that because I can have all the information in my graph. I have not only the rings, but I have also the connections between the nodes of the graph, my atoms, and that are going to be my bonds. Okay. We plot them together, right? And then we plot them according to the rings. And let's do that all in one nice thing here. And look a little bit more into how stable is this method, right? I mean, for a honeycomb kind of pattern, obviously the positioning is quite easy. Also, if this, if I have slight distortions, which I have minimized before, I get that very accurately. They are very close together, and I probably don't have a lot of problems with that. The defects are a different matter, so I want to have those very accurately. And so I can play around with it now. And so what I'm doing is I'm changing the positioning, the distance between those, and see whether it works. So if I extend it, up to 0.25, you see how large this atom, this bond is, and how short this one is. So it's independent of how large that bond is, because it's only depending on the rings. Let's go in the negative, put them very close together. Okay. Yep. Nice. No problem. Always the same idea. So independent of distortion, you can shear it, of course, or whatever. If you do it too large, what happens then? So I put 0.35 in here. Okay. Is that reasonable? Yes. So here is my convex polyhedra. No polyhedra, polygon. And then here I cannot make one. So here it's going a little bit in. So you see, we have not longer a convex one. So it's stepped in here. And so now I have 3 triangles instead of a 5-fold ring. And and this one is now a 6-fold one. Key thing is no input. And you get your bonds. And it's unambiguous. And the only things that we are really looking for is convex polyhedra. How does a vacancy look like? Well, if you don't relax your vacancy, you will get a triangular feature here in 5-fold rings. If, say, and that is to the convex part, right? If these atoms, as they should, relax in and out, you will actually have a convex one, and then you will have whatever 9-fold ring here. So depending on that. If we do a relative complicated one, so it would be strontium titanate in the 1,1,0 direction. So we know how to do strontium titanate. And I just do the same thing as I did before. We can do different ones here. But we use strontium titanate. And I go into the 101 direction, get a projection. And that is it, right? And then I make a ring graph out of that, as I did before. Then I get my rings. I get my centers of the ring. Right? And I get my ring, get my bonds. Everything nice and easy. Okay. There are a lot of different Voronoi positions there that is in here. So actually for each of the cell, okay, I wanted to be in that graph here. For each of the cells, we have actually, I think 6 or 7 Voronoi graphs. So here's one, there's one. Okay, so there are many of those. And instead of just using, in this case, it was a nearest neighbor search tree from SciPy Spatial, I can also use any of the cluster algorithms that we did before. And so what I'm doing now is I get these new vertices by using a density scan or density clustering from scikite-learn. And so we have in my lectures, the first one that we're doing here. And we get, of course, exactly the same result. So we find the atoms Voronoi centers based on a density scan. What do we have to put in here? Not as much as if we do that with where's my density scan? Yep. Put the minimum Voronoi distance here. And I really use it only as a vague input now instead of a hard input of how close they should be. The minimum sampling size is 2, so everything else is a single one, and I'm using Z to determine that as well. The other ones are averaged. Okay, so sorted in clusters, and of course, if you do it a little bit more sophisticated, as in the Python lib, then you get this one here, and you can see the only difference is that I can go all the way out to the edges, and I get my rings very, very accurately. Okay, so a bit faster than I thought I would get through, so there might be a lot of questions. Let's go through the questions and see whether we have any. Okay. I can hear. Okay. Okay, there's not any question right now. Yeah. Doesn't look like. Sergey, say something, please.
So how robust is the daemon registration if one atom disappears? So you have a graphene stack, you try to register it, and then atom gets kicked out? Is it going to ignore it, or is it going to somehow spread the missing atom among others? You are muted, Gerd.
Okay, I'm muted again. Okay, so the daemon registration is based on the area, right? It's not all based on the atom, and so if the area in the vicinity is it will distort everything similarly. If it doesn't have enough information, it will just leave it there. So that is very robust against any of those kind of events. Ideally, of course, that is a data set that you wouldn't use any further. So ideally, you would want to stop it, the stack, when these kind of events happen. Of course, sometimes you cannot, but the area certainly is not longer an original area and shouldn't be used. But the daemon registration will just put it through. There's no problem with that. It's very I would call it error tolerant with respect to that. Okay, there's one new message, and I don't know where my, oh, here we are. Okay. Okay. So again, this is not a stack that you should be using. Okay, do we have any other questions? It was quite a run through. So there are a few powerful techniques, and all of those can actually be combined with other machine learning techniques. So that's the idea behind it. And the quantitativeness of the whole thing is, of course, the key. So you're not only getting positions, you get how accurate are they. Do we have any more questions? Don't see my chat anymore. Oh, here it was. A second. My computer is slow. Okay. Yeah. So the Demon registration is also very resilient to different kinds of intensity variation. So that is also a nice thing about it. Interesting. Okay, if there are not more questions, then that is the end of this lecture. And I would encourage you to try them out. They are very robust techniques. And as I said, I even work with them on 3D models for material simulations with this kind of graph theory techniques. Very powerful. Okay, so the next lecture will be on dimensionality reductions in images. So machine learning on images, very simple, or not very, relative simple techniques. Then before we go into the 4D STEM machine learning part, I will introduce also diffraction. We have another part, and then I will do one on STEM, also C-contrast image simulation, where, of course, we also need the diffraction part, and we learn about the thermal diffuse contrasts. Okay, thank you for your attention, and well, hope you have a good day.